We've been talking a lot about relationships within triangles so far. We talked about angle bisectors and perpendicular bisectors and medians, and we talked about now mid-segments, and in all of those cases we have relationships that are true and some things that are equal to something else or double something else. Today, instead, we're going to be looking at a different type of relationship. We're still dealing with triangles and relationships within triangles, but today we're going to be talking about inequalities within triangles. I think a lot of the theorems, or the couple theorems that we're going to look at today, actually make a lot of sense. They're pretty intuitive. We can reason out why these things must be true, and so that means that we can really make sense of a lot of the theorems in the context that is presented. So the first one that we're going to look at today is called the triangle longer side theorem. And what this says is that if we have a long side or a longer side of one triangle, then the angle opposite of that longer side is bigger than the angle opposite of the shorter side. What that really means is, if we have a long side, then we have a bigger angle that produces that long side. And if we have a short angle, we have a shorter angle, or a smaller angle that produces that shorter side. The key here, though, is recognizing what the angle is that's opposite from the sides that we are dealing with. So in a triangle, just for example, I'm going to call this triangle DEF. If I were going to talk about this side length, EF, the angle that's opposite of EF is angle D. So EF is opposite of angle D, or angle D is opposite of side length EF. DF is going to be opposite of angle E, and DE is opposite of angle F. Another way to look at that too is that EF, these two vertices here of my triangle, contain these two vertices, but angle D, or point D, vertex D, is not part of that segment, so it's going to be the one that's opposite of it. So in my triangle DEF, if I'm talking about segment EF, it's going to be angle D because that's the vertice that I'm not using to talk about my segment EF. It's the one that would be opposite. So you have to look across your triangle, and that would be the angle then across it. So if this angle is smaller than, say, this angle, that means that the side length across from my bigger angle is going to be bigger than the side length across from my smaller angle. So in this situation up here, if I have a side length here that's 8, and I have a side length here that's 5, 8 is bigger than 5, so that means that my angle across from 8, which is angle C, is going to be bigger than my angle across from angle 5, side length 5, my side length BC, which is angle A. Okay? Bigger side length produces a bigger angle, smaller side length produces a smaller angle. And then the converse of that theorem is also true. So this is the triangle longer side. So that means that you're presented with some side, and then you talk about the angles. You are making some sort of conclusion about the inequality that is with those two angles that we are comparing. But the converse is also true. So in my larger angle theorem, we are going to be given some angle, and then we can make a comparison about the side lengths. So it's just the converse of that theorem. If we have an angle that's bigger than another angle, then the side length across from that bigger angle is going to be bigger than the side length across from my smaller angle. So in this example here, the measurement angle A, which is 50 degrees, is bigger than the measurement angle C. The side length across from my angle A, which is 50 degrees, is side length BC, and that thing is going to be bigger than my side length across from my angle C, which is 30 degrees, and that's AB. Okay, so BC is going to be bigger than AB. So that is kind of intuitive. As I'm opening up, a pair of scissors, and my scissors is getting, my scissor angle is getting wider, my side length, or the thing, I would connect the 2 points of my scissors together, that would be getting bigger too. So a bigger angle, bigger side length. Pretty intuitive. Makes a lot of sense. Those are two of the theorems that we're going to deal with today, is just, bigger angle, bigger theorem, or bigger angle, bigger side length, or bigger side length, bigger angle. The converse, both of those, it goes both ways, a bigger angle or a bigger side length. The other theorem that we're going to look at today is called the triangle inequality theorem. And this theorem is pretty important because it defines what could be a triangle. Now, not all lengths that we could deal with or that we could just spout out could make a triangle. There are certain lengths that don't work. So, in order for lengths to form a triangle, to connect in a section, so for example, like this length and this length and this length, there's no way to connect those into a triangle. So we have to have something that's true. There should be some like tipping point that makes some triangle as we connect it. Like there's only so many times or so many ways that we can connect these three different lengths in order to form something. So that theorem tells us that, or what the theorem says, is that the sum of the lengths of any two sides of the triangle has to be greater than the third side. So if I was looking at these two side lengths, I would have to know that AB plus BC, if I line them up, these two side lengths have to be bigger than my third side AC, or B angle, or side length BC and side length AC, if I line them up, have to be bigger than my third side of AB, or my side length AC and side length AB, if I line them up, have to be bigger than my side length BC. All those things have to be true, which seems like a lot to test. Because if I am dealing with some triangle, it seems like I have to test all three different combinations, but there is a shortcut. Instead of testing all three, we are going to test, or we're going to cut this down so that we're only testing the two smallest. So this means that the two smallest sides must be greater than the largest side. So most often, this is how you'd see it in an example. So it might say, could the lengths 3, 4, and 5 form a triangle? Because not all lengths can. Some lengths, like these three lengths, there's no way to connect them to form a triangle. That would not work. So we're asking, could the lengths 3, 4, and 5 form a triangle? So instead of testing the combination of 3 and 5 being bigger than 4, and 4 and 5 being bigger than 3, and 3 and 4 being bigger than 5, all we really have to do is test the two smaller ones. So our question is 3 plus 4 bigger than 5? And if that's true, if these are the two smallest and we test it against my biggest, if that's some inequality that works, which this one is, 7 is greater than 5, then yes, it forms a triangle. Now, if we get something that is smaller, like on this side, let's do another one. So we're going to see, could the lengths 1, 2, and 3 form a triangle? In this case, if I'm testing my two smaller, so our question is 1 plus 2 bigger than 3? So for this one, we get 3 is bigger than 3, which is not true. So no, these lengths couldn't. These couldn't form a triangle. So if we get something that's less than over here, obviously that wouldn't work. And also if we get something with the same number, like 3 is not greater than 3, that also doesn't work. So this example would not work for a triangle, but this example would. And this is also, like, if you forget how to actually make this case or figure out what the inequality is, I always go back to this triangle because I know this triangle. You might too. Like, this is a really common Pythagorean triple is what that's called. It's a right triangle. It satisfies the Pythagorean theorem. So you might know that one, 3, 4, 5. And so you might want to think about that one, that triangle. This triangle does work. And so that will help you remember what the inequality says. Okay? Or you could just draw a picture and you can think about those lengths and convince yourself that it's actually, 2 sides is bigger than this third side. So we are skipping part of this section. We're skipping like these examples of the indirect proofs, and we're just going to deal with the listing the angles from smallest to largest and deciding whether we could construct a triangle with these given side lengths. And then we're going to do a couple of extra examples to help you with your worksheet tomorrow. Okay, so these theorems, this theorem goes along with the larger angle, the two that we started with, the triangle larger side theorem, and the triangle larger angle theorem. So we're going to list the angles of the triangle in order from smallest to largest based on the side lengths that were given. So this means that we're looking for a bigger side length to produce a bigger angle. So since I'm going with my smallest to largest, I'm going to look for my smallest side length first because that's going to produce my smallest angle. So my smallest side length in example 6 is 6, which means that my angle across from that side length AB is going to be angle C. So that's going to be my smallest angle. And then my next smallest side length in order would be 8. So the angle across from that side length 8 is going to be angle A. And then my largest side, which is 10, is across from my biggest angle, which is angle B. That's one way you could write it. Or you could say that the measurement of angle C is less than the measurement of angle A, which is less than the measurement of angle B. That's a possibility too. So you might see it written in that inequality sense, that like this angle is the smallest, it's less than this one, which is less than that one. If you're going to do it that way though, you have to put the measurements there because these are talking about numbers. So this says like list them in order, but this would also be like a list, but it would be with the inequalities. But you have to put your measurements there if you're going to do it that way. Might as well just put it in like, separated by commas. So for number 7, my smallest side length here is 7, so that's across from my angle D. So angle D is going to be my smallest. I should write that here. Smallest. This is smallest. And largest. My next smallest side length, or my next biggest side length is 15, which is DF. That's across from my angle E. And then my biggest angle is across from my biggest side length, which is 18, DE, so that would be angle F. That's my largest. Okay, last one. My smallest side length that I have is 11. That's across from my smallest angle, which is H. Moving up after 11 goes 14. That's across from my next smallest angle, which is angle J. And then my biggest angle is across from my biggest side length, which is 16, so that would be angle G. And I think that really makes a lot of sense. I think it's pretty intuitive. Bigger side length, bigger angle, bigger side length, smaller angle, smaller side length, smaller angle. Okay, this next section is the triangle inequality theorem, which tells us that we only can have certain amounts of side lengths that will produce a triangle, and we have to test. Again, we're testing the 2 smaller ones. So for this one, we're deciding is 3 plus 12, is that bigger than 17? That's our setup for our inequality. Well, 3 plus 12 is 15. Is 15 bigger than 17? No, that's not true. So it's not possible for that one. 3, 12, and 17 will not form a triangle. And we don't have to test like 12 and 17 bigger than 3 because we know that that one works, and we know that 12, what we do, 3 and 12, 12 and 17 is going to be bigger than 3, and 17 and 3 is going to be bigger than 12, but 3 and 12 isn't bigger than 17. That combination doesn't work, and so since one of those combinations doesn't work, then we don't have to test the other ones. It won't form a triangle no matter what. All those things have to be true, which is why we're just testing the 2 smallest ones, because the other ones probably will work. So if we just test the two smallest ones, then that skips those possibilities. So again, same thing for the next one. We're deciding these are my two smaller ones, 5 and 16. I'm going to decide if I add up 5 and 16, is that bigger than 21? Well, 5 and 16 is 21. Is 21 bigger than 21? No, it's not. So that one wouldn't form a triangle. Okay, next one, 5 and 7. Those are my two smaller side lengths, or two smallest. So we're asking, is 5 plus 7 bigger than 8? Is that a possibility? Does that work? Well, 5 plus 7 is 12. 12 is bigger than 8. That does work, so yes, this one will form a triangle. And our last one, our two smaller side lengths are 10 and 3. Is 10 plus 3 bigger than 11? Well, 10 plus 3 is 13. 13 is bigger than 11, so yes. And all of our reasons here are, explanations for why this does or does not work. It's satisfying the triangle inequality theorem. So these don't satisfy the triangle inequality theorem, but these do. So we can build a triangle. The other combination, or the other way that this could be asked of you for the triangle inequality theorem, is to decide if, or list the possibility for this next example, list the possibilities of our third side length given 2. Can we come up with a combination of possible side lengths for the third side of our triangle? So definitely, if these are my two smaller side lengths, then I'm going to say, like my third side, I'm going to label that as x. So if I know that these are the two smaller, so 5 and 13 are the smallest, or the smaller ones, and x is going to be the bigger, then I could come up with an inequality that would represent those. Like my two smaller, 5 and 13, would have to be bigger than my third side of my triangle, which is x. So that would be 18. So that's one possibility, that 5 and 13 is, those are my two smaller. So I would have that x has to be less than 18. But I just assumed that 5 and 13 were my smallest sides, and they don't have to be. Like, what if 13 is my biggest? So my other possibility is that 5 and x are smaller, and then 13 is the biggest. That's the other possibility, is that 13 is actually on the biggest side of my triangle. 5 can't be the biggest because we already know that 13 is bigger than that. So the other possibility is that 13 is biggest. So that would mean, if I use the triangle inequality theorem, that 5 plus x, my two smaller sides, have to be bigger than 13. And if I solve for x and subtract 5 on both sides, then I get that x has to be bigger than 8. So all around, if I'm going to combine these two, you could list them separate if you want, or you could list it as one called a compound inequality, where x has to be in between. It's bigger than 8 but smaller than 18. So we could write it this way, that x has to be between 18 inches and, 8 and 18 inches. If you notice, a shortcut for this too is that we actually got 8 by doing 13 minus 5, and then we got 18 by doing 13 plus 5. So you can do that too to find your endpoints. Like 13 minus 5 is going to be our smallest endpoint that it could potentially be, and 13 plus 8 is going to be our largest endpoint that it could possibly be. Okay, so that's what in the student journal. You should have gotten an extra example sheet, so we're going to look at those two. The extra example sheet, the question is saying, list the side lengths in order from smallest to greatest. So we've already done this with angles. We are listing the angles in our triangle from smallest to largest. We are going to list our side lengths this time in order from smallest to largest or smallest to greatest as well. So that means that if we're going to list our side lengths, we need to know something about our angles. So if I know that like angle A is smaller than angle B, then that means that side length BC is going to be smaller than side length AC. However, in this problem, we don't know anything about our angles right now. Like, we just know that we have like 3 angles that are listed in our triangle, but we don't know the actual measurements. So that means we got to solve for the measurements first. Now for this one, since I'm given all 3 angles of my triangle, I know that according to the triangle sum theorem, that all 3 angles have to add up to 180 degrees. So that's what we're going to do first, is add up all 3 of my angles to 180 and solve for x. And once I solve for x, then I can plug it back into my angles and then find out my measurements there. So I have 5x plus 6x, which is 11x, plus 1x, which is 12x. I have 2 minus 10, which is negative 8, plus 20, which is positive 12. That equals 180. Subtract 12 from both sides. And we get 168. And then we can divide by 12. And we should get that x is equal to 14. So now that we have x, we can plug it into our equation. So I can solve for the measurement of angle A by replacing 15 or x with 14. I can solve for the measurement of angle B by replacing x with 14 again. And I can solve for the measurement of angle C by doing the same thing, 14 plus 20. So this one I'll get 34. I'll solve for my other ones. And I got these 3 angles, and you can double check and make sure that all 3 of those angles do in fact add up to 180 degrees, and they do. 72 plus 76 plus 34 does add up to 180. So let's see, there we go, there's 74 and there's 72. I'm going to replace that. And now I can use those angle measurements to list my sides in order from greatest or smallest to greatest. The smallest side length that I have would be across from my smallest angle, which in my case, the smallest angle that I have is 34. So that means that AB has to be my smallest, oops, write it down here. AB has to be my smallest side length. And then my largest side length has to be across from my largest angle, which is 74. So that means that AC is going to be my largest side length. So then the intermediate side length that I have is across from my middle angle, which is going to be BC. Okay, so it's like the same idea that we just did with listing the angles in order from smallest to largest. This is listing the sides, but we need to know anything about our angles. So that might mean that we have to solve for a triangle first, rather than just like looking at the angles. We might have to do something for it first. Okay, same thing for number 2. Like in this example, we're listing our side lengths in order from smallest to greatest. We have this triangle here. I don't know my angles, but I do know some things about them. I do know that this angle here is 2x, this angle is 50 plus x, and this is 5x minus 2. Now this is not the same as example 1. We're not using the triangle sum theorem here because I don't have all 3 angles inside my triangle, but I do have an angle outside my triangle, which is an exterior angle. So for this one, I can use the exterior angle theorem, and that tells us that we add up our 2 non-interior or non-adjacent interior angles, 2x and 50 plus x, and that has to equal the exterior angle that's given, 5x minus 2. So on this side, I'll have 3x plus 50. On this side, I have 5x minus 2. And I can solve for x, subtract 3x from both sides. And I get 2x, add the 2 over. And then divide by 2, and we should get 26. Oops. So then we're going to come up with all the angles in my triangle. So our first angle that we have is here. So this is angle, I originally called it angle A, but I can't call it that. I have to call it angle ABC. So this angle is the supplement to this angle here. So if I plug in 26 to my exterior angle that I have, 5 times 26 minus 2, I can come up with that angle, which will end up being 128. And then I can find this angle by doing the supplement, so I'll subtract 180 from that angle, and we should get 52. So the measurement of angle BAC is going to be 52 degrees. I can plug in 26 here and also get 52. And my last one, 50 plus 26, is going to be 76. And again, you should probably double check and make sure that all those angles do add up to 180 degrees, which they do. So for this one, it's kind of interesting because my two smaller side or angles that I have are actually equal, which means that if I'm going to write a list of smallest to greatest, since these two angles are equal, then these two side lengths are equal. And that actually should make sense because this means that, like with my converse of my base angle theorem, if my two angles are congruent, then the sides opposite my two angles have to be congruent as well. And we can see that with my my triangle inequality theorem too, because, or my triangle larger angle theorem too, because I have a smaller angle, which means, or these two smaller angles that are equal, which means that the sides opposite of them must be equal to. Like I can't have, if this angle is equal to that one, then there's no way for like this side length to be bigger than that side length because that angle would have to be bigger than this angle, which it's not. They're equal. So that means that AC is going to be congruent to BC. And those would be my smallest ones. And then my largest, these are my smaller. My largest has to be across from my larger angle, which is 76. So that means that AB has to be my largest side length. So that would be my answer for that one. It's a little bit weird because we've been listing them in lists before. But for this one, since we have the two congruent or two equal sides, our list actually looks something like that.